Hi, I'm John Norman, the retired Chief of Special Operations for the FDNY. For more than 36 years, I've been fighting fires in rural, suburban, and urban areas. Modern firefighting is a continually evolving science. New technologies are constantly being introduced, such as new chemical compounds, locking devices, and entry tools. But the strategies of modern firefighting have not changed. The basics, protect life, confine the fire, and extinguish, are constants. Each firefighter has the responsibility to keep informed of new developments in the fight against fire. That's why continual training and learning is essential. The Fire Officer's Handbook of Tactics DVD series will take you through the necessary steps to help you become a great fire officer. It will give you the strategy to become a better leader and provide you with the best methods for handling specific situations. Today, we will discuss ventilation. You will learn about the science of ventilation, different types of ventilation, what tools to use, and some common mistakes. As many of you know, there's more to firefighting than just getting into the building. The challenge is being able to stay inside long enough to complete your mission. The fire is filling the structure with such thick, dense smoke that many times it's impossible to see. Soaring temperatures will burn unprotected skin and ultimately can be deadly. You must also fight to stay ahead of the moving fire, which is constantly in search of more fuel and more oxygen. Think of it this way. You and the fire are battling it out for the same thing, oxygen. Whoever controls the oxygen supply wins the battle. Ventilation is a big part of this warfare and a key factor in deciding whether the building is saved or burns to the ground. Ventilation can be defined as the process of removing toxic products of combustion and replacing them with fresh air. I like to define ventilation as an ongoing battle between the fire and the firefighters for control of the building. The fire is constantly pumping deadly toxins and flammable gases into the building. Your job is to use the right weapons at the right time to defeat this assault. There are two main reasons to ventilate: to allow the attack team to enter and operate inside the structure, or what we call venting for fire, and to provide fresh air for breathing and to improve visibility while searching, or venting for life. Unfortunately, some firefighters forget the difference, or even worse, the need for ventilation in the first place. Because SCBA is so common, some people think that ventilation isn't as important as it used to be, because our firefighters can breathe. But there's a real problem with this. First, it totally ignores any victims that might still be inside. Second, they assume that their masks will always protect them, and unfortunately, that isn't always so. Several firefighters have been killed in recent years when they've had problems with their masks in contaminated areas. They ran out of air, got entangled, or had their face pieces pulled from their faces. Also, remember that your mask is designed to protect you against smoke, but not heat or flame. The difference between venting for life and venting for fire is the timing of the ventilation. By this, I mean if you determine that there are lives at risk, you should begin venting for life as soon as possible. Keep in mind that once you begin venting, the fire may intensify, but if done correctly, the venting will draw the fire away from the life hazard. Take, for example, the crowded apartment houses, so commonly found in many cities. In New York City, one member from each of the first two ladder trucks immediately goes to the roof and performs ventilation over the interior stairway and any other vertical shafts. They do this without orders at every working fire. This draws the fire out through the top, into the open air, instead of allowing it to mushroom on the upper floors and spread into those apartments. Immediate vertical ventilation has saved hundreds of lives by drawing the fire away from the victims. It should be the primary ventilation tactic at most low-rise, non-fireproof apartment houses or multiple dwellings. On the other hand, venting for fire is usually delayed until resources are in place to attack the fire. For example, if you respond to a heavy smoke condition pouring from a second-floor apartment in a 4-story apartment house and you're having trouble with the nearest hydrant, you should hold off on performing horizontal ventilation until the charged hose line's in position. Once the attack has begun, you can vent the windows opposite the hose line, allowing the products of combustion to be blown ahead. There are many different types of ventilation and different results from each of them. In the example I just gave you, the horizontal ventilation functioned as venting for fire. It can also be used to assist in saving lives. Here's how. If a person is in a room adjacent to the fire area, venting the windows will bring in life-saving fresh air. However, if you don't remove the victim right away, you may worsen the situation by drawing the fire toward the vented window. If you use horizontal ventilation for life, either bring in a hose line to protect the victim or, if possible, remove the victim. The most important part of ventilation is the proper amount of ventilation. If the fire is of low intensity, such as a smoky mattress or food on a stove, you should open the windows, not break them. Window ventilation is best for most house fires or other structures that have similarly high window-to-room size ratios. It's very quick and relatively easy to do, and it can be targeted to specific rooms. The guide I use is if you can stand up long enough to manipulate the locks, then raise the windows. If you can't stand up for that high or for that long because of the heat, then it's time to take out the glass. This is a good rule of thumb, but there are a few additional points to make. First, find out if the fire is under control and if search efforts are complete and no victims were found. If that is the case, you can raise the window instead of breaking the glass, even if the area is warm to hot. On the other hand, if a victim is missing, if the fire is extending, or if there is a very dense smoke condition, you should break the glass, even if it's not very hot. Venting not only provides fresh air to victims, it improves conditions for firefighting, leading to earlier control. Also, firefighters are less likely to become disoriented or trapped if visibility improves. When you break out a glass window, it gives you twice as much window opening area as raising a double-hung window. Obviously, once you've broken a window, you can't reverse it, so timing is everything. Venting too early will allow the fire to grow, but delaying ventilation will cause unnecessary heat for the firefighters. Generally, you should vent for fire attack just as the hose line begins its attack. It's best to coordinate this by radio. A member of the attack team should give the word to take the windows, just as they open the nozzle. One big exception to this sequence is in the case of double or triple pane energy-efficient windows. In this case, a sudden rush of oxygen can cause a backdraft. If you encounter energy-efficient windows, vent the windows as soon as possible while the attack team is in a safe area, preferably behind a closed door. If that isn't possible, wait to vent until after the hose team has thoroughly cooled the fire area. Other factors that will help you decide whether to use vertical or horizontal ventilation, or both, include the size and location of the fire, the construction of the building, and the wind. Horizontal ventilation is preferred at minor to moderate fires. A mattress fire will produce a lot of smoke, but will not be hot enough to make the smoke rise very far. Therefore, vertical ventilation wouldn't be a good choice there. Many times, horizontal ventilation is faster and easier to perform than vertical ventilation because there are already openings, such as windows and doors. Plus, it can often be carried out from the ground level or from a one-man portable ladder. Vertical ventilation usually requires a longer ladder and more manpower to get to the roof. Another plus to horizontal ventilation is that it costs less to repair than vertical ventilation, unless, of course, there are already man-made openings on the roof. Glass is much cheaper to replace than a section of the roof. The type of roof will also help to determine the type of ventilation required. Peaked roofs, found on many homes, are usually easier to vent by using the windows in the gable ends or dormers than by cutting the roof, while flat roofs of poured concrete would be extremely difficult to vent in any case, unless a built-in opening such as a skylight already exists. This doesn't mean that vertical ventilation is less important than horizontal, it just means that it has its place. Vertical ventilation can be a deciding factor in whether the fire is stopped or continues to expand. When materials burn, they release hot gases, which take up huge amounts of space, usually hundreds of times the volumes of the original burning material. This gas tries to rise, and when it can't, it spreads out horizontally. You need to create a way for this mushrooming gas to go straight up and out of the building, taking a lot of the heat with it. When you vent large amounts of this hot gas horizontally, it flows under the ceiling toward the open window, spreading heat in this direction. When this happens, other combustibles are being preheated, as are the firefighters trying to approach. In these circumstances, if you make the right size opening in the roof, the relief is dramatic. Fire moving horizontally can be stopped, and visibility and heat conditions improve almost immediately. As I said earlier, not every fire demands or even allows for vertical ventilation. Fires that are relatively small, as well as those in lower portions of the structure, far away from vertical openings, probably won't benefit from opening the roof. On the other hand, roof venting would be a good choice for fires in attics and cocklofts. Now let's talk about mechanical ventilation. To do this, we need to back up and remind ourselves how ventilation works. When fire heats up combustibles, the byproduct, what we call smoke, begins to move. When we open doors and windows, the smoke naturally pours out. This is called natural ventilation since it's based on a natural action of heated gas. Sometimes this natural process is not enough to move the smoke quickly enough to let the firefighters do their job. In the case of a smoldering mattress or a low heat fire in a basement, the smoke may be so cool that normal ventilation won't work. The smoke will hang down low, keeping the deadly carbon monoxide with it. Another time this occurs is when a fully developed fire has been knocked down by a sprinkler system, but isn't fully extinguished. In all of these cases, it's best to use mechanical ventilation to move the gases that otherwise wouldn't move easily. Mechanical ventilation can involve hose lines, portable fans, or building ventilation systems. Venting can be done by either sucking out the bad air or by blowing fresh air in. There are pros and cons to both methods. A very effective means of mechanical ventilation is the fog or spray stream. It doesn't take much manpower and is easy to use. It works by the spray of water carrying air along with it. Several factors affect how much air and smoke the stream can move. The first is the amount of water flowing, since each drop of water brings along a limited amount of air. The more water flowing, the more air is moved. The second is the velocity of the stream, which relates to the pattern of the stream and the nozzle flowing pressure. The higher the nozzle pressure, the more air that is moved. The best pattern to move the most air from an area is one that is tight enough to move the stream of smoke, yet wide enough to carry large amounts of air. This is usually a 30-degree pattern. The last factor is the geometry of the opening in a stream. If you stand back from the window about 6 to 8 feet and adjust a pattern to just cover the opening, you'll create a Venturi effect, which will make the stream much more efficient. Sometimes, standing this close won't work, especially in a larger area with smoldering material behind you. Once you begin to ventilate, the fresh air moving toward the nozzle can cause the smoldering material to burst back into flame, drawing all the smoke and heat right past your nozzle team. In this case, it's best to stand further back and use a narrower stream to reach the door or window. One concern with any type of mechanical ventilation is this danger of fanning a smoldering fire back to life. That's why using a hose stream gives you an advantage. You can keep an eye on the fire and use the hose stream to darken it down if it flares up. Of course, you can't use the hose stream everywhere. It shouldn't be used at minor fires where water damage is a concern, or in areas of poor water supply, or in below freezing temperatures. Smoke ejectors, blowers, exhaust fans, and other portable devices don't have the same drawbacks that the hose line does, except the problem of a forced draft over smoldering fires. However, as convenient as these devices are, you should prepare yourself for the possibility of power supply issues, manpower problems, storage space, or the threat of explosive gases. As we've learned, mechanical ventilation is a great way to move the bad air out of a structure. There are devices that suck smoke out and those that blow fresh air in. Exhaust devices, or those that suck smoke through the mechanism, don't work as well for several reasons. First, they never fit an opening correctly, so they lose efficiency as air moves around the sides of the units. Also, debris such as curtain and other objects can be sucked up against the intake screen, which will block the flow. And they must always be set up in or near a doorway, which hinders your ability to get in and out of the structure. And because they blow outward, combustible gases will be drawn across the motor, which could be dangerous. Fans that blow fresh air in work much better and eliminate many of the problems I just talked about. Originally, these types of fans were tested as a way of reducing stack effect, which is heat and smoke being drawn towards staircases, which is the point of attack in high-rise fires. Experience has shown that by putting a positive pressure in a stairwell, the flow of heated gases can be reversed, which will enable the attack crews to gain a foothold on the fire floor. This concept also works on many structures other than high-rise fires. Positive pressure ventilation, or PPV, has advantages over negative pressure in many ways. With PPV, the fan is set up outside the structure, about 8 to 12 feet away from the door. The fan is aimed so that a stream of air completely covers the door opening. You may have to use several fans for larger doors in commercial buildings. The moving airstream carries more air along its sides as it flows, acting as a venturi to bring in even more air as the stream passes through the opening. When the air moves into the structure, it pushes the smoke-contaminated air ahead of it. A fan blowing in can move almost twice the volume of smoke compared to the negative mode. The Los Angeles Fire Department conducted tests that show you get the best results by clearing a structure one room at a time. Open the windows in the first room to be cleared, then close the window or door to isolate that room when you're finished, and move to the next room. When you set up the fans, keep in mind any natural wind you may encounter and try to work with it, not against it. This method works best with minor to moderate fires where smoke is the biggest problem. When you have an advanced fire that is self-vented, the effectiveness of the airstream from the fan may be reduced by outside air movements due to the fire-vented openings of a large number of windows. Fires that are partially extinguished by a sprinkler system, mattresses, stuffed chairs, and other extra smoky fires are all good candidates for positive pressure ventilation. Since PPV fans are set back away from the doorways, they won't get in your way. Another advantage is they can also remove flammable vapors safely and quickly, since the gas is not drawn through the fan. As with any firefighting technique, PPV does have some problems. The biggest is the danger of fanning smoldering fire into a serious blaze. The best way to prevent that is to have a charged hose line in place and ready to go. This can be a challenge in arson situations with multiple fires, because the hose line may be in place for one fire while another one grows from the effect of the draft, usually undetected until it's much larger. Another concern when using PPV, you must be sure the fan doesn't blow the fire toward any victims or firefighters on the opposite side of the fire. For this reason, don't use PPV if firefighters are entering the building from areas other than where the fan is set up. If you suspect a life hazard, you will not be able to use PPV immediately. When searching for a victim, you will have to vent as you move, which is the exact opposite of what you would do to make PPV work effectively. When you're making the decision whether or not to use PPV, you must consider other factors, such as the extent of the fire, the location of any life hazard, the availability of hose lines, the degree of confinement, the power supply, and the possibility of debris being sucked into the fan. If the situation is right, then PPV can make your job much easier, but you have to be ready to shut down the PPV if it begins to have any negative effects on the firefighting. Let's talk a little more about vertical ventilation. The natural tendency is for heated gas to rise. When it cannot do this, it will spread out horizontally, which is called the mushrooming effect. There are several ways to prevent this horizontal spread. Build a fire-resistant partition, position a countering hose stream, or let the gas continue going upward, where it wants to go anyway, which works best in multi-story structures by making an opening directly over any vertical arteries that the fire is heading towards. The most common vertical artery is the staircase. If you make a large enough opening at the top, the fire will continue upward without extending horizontally. You should look for buildings where this is possible, and if there is a serious fire, make every effort to vent this area as soon as possible. Some buildings even have skylights over the staircase. If this is the case, you can break the glass panes, which will provide quick ventilation. Before you do this, though, remember to warn other fire personnel down below that you're getting ready to break the glass. Break a single pane first and pause momentarily. If you or one of the members down below, keep your head level and don't look up or down. You should also stay as close to the wall as possible, keeping your arms and hands close to your body. Also, keep in mind that some staircases continue past the top floor, ending in a small bulkhead with a door leading onto the roof. You will need to open this door for additional ventilation, but even more importantly, to check the roof landing for any fire victims that attempted to escape to the roof. Other vertical paths for fire travel are pipe chases and dumbwaiter shafts. Dumbwaiters are small, hand-operated mini elevators that were common in multi-story residential buildings built in the late 1800s and early 1900s. Most of these are no longer in use, and some have been replaced by compactor chutes, but the shaft will still be there. Any fire that makes it to one of these shafts will quickly zoom to the top. Check to see if there is a door or skylight at the top of the dumbwaiter shaft, and if there is, open it to allow the fire to escape. The pipe chases are usually found behind kitchen and bathroom walls and extend right up to the underside of the roof boards, where a single vent pipe, called a soil pipe, extends through the roof. This pipe will give you a good idea of where the vertical arteries are, and if the pipe is hot, it will also tell you the fire could be in the attic or cockloft. Now let's discuss venting flat roofs. Flat roofs are usually found on larger buildings, such as stores, factories, schools, and apartment buildings. There are two primary types of flat roofs, the old-style flat roof and the metal deck roof. The old style can be designed as either a standard flat roof or an inverted roof. Older flat roofs have wooden beams of 2x10s or even 3x12s as the main support beams. These are usually spaced 16 inches apart and can carry the same loads as the floor joists below them. They are limited in length to about a 20-foot span between supports, which is usually either a masonry bearing wall or a steel I-beam. Nailed directly to these roof beams is the roof decking, usually 1x6 tongue-and-groove boards, or on newer buildings, plywood. The roof decking is then covered by layers of tar paper and then mopped with hot tar to seal it. Sometimes gravel was spread over the hot tar. In some very old buildings, the tar paper can be up to 4 inches thick, making it difficult to cut through. These are relatively safe roofs to work on, even over a heavy body of fire, due to the mass of the supporting beams. The roof boards will burn through first, before there is any danger to the supporting joists, which makes catastrophic roof failure unlikely. It is possible, however, to step through the deck if the roof boards are weakened, which could plunge the firefighter's foot or leg right into the flames. A working fire on the top floor of any large area, flat roof building needs at least 4 men equipped with 2 power saws, 2 6 or 8 foot pike poles or hooks, a Halligan tool, an axe, and at least 1 portable radio. If possible, an officer experienced in roof ventilation should also be assigned to this location. As soon as you get to the roof, you should begin venting any vertical shafts you can find, such as bulkhead doors or skylights. You should also vent the top floor windows by striking them with a hook or a Halligan tool tied onto a rope. Only after you have vented the stair and other shafts and the top floor windows should you begin roof cutting. Do this by getting as close to the area over the fire as is safely possible. Do this only after you evaluated the condition of the roof and the danger of collapse. Sometimes locating the fire takes some investigating. Fire coming out the windows is a good indicator, while smoke may not be as reliable. You can also look at the surface of the roof for bubbles in the tar, or steam, or by cutting examination holes. There are 2 common types of examination holes, a triangular opening or a short, narrow slit called a kerf cut. Both of these cuts are made with a power saw. The kerf cut is the fastest and easiest type of examination hole, plus it's easy to repair if need be. Just plunge the saw through the roof and pull it out. You'll make an opening of about 1/4 of an inch by 10 inches long. Because the opening is so narrow, it can be difficult to see the fire, especially during daylight. The triangular cut is a little more time-consuming, but it's easier to see the fire. Just plunge the saw through the roof 3 times so the edges of the cuts overlap. Once you've chosen the right location, make everyone in the area aware of what you plan to do. Plan an escape route off the roof in case things go badly. You should always have at least 2 ways off the roof. When you make your cut, make sure it's not between the members and their only means of escape, or else you could become trapped on the roof. Also, be aware of the wind direction. The wind can blow the smoke or fire in such a way that it could block your escape, and wind will change direction at some point during the operation. The saw operator must be able to cut with both the left and the right hand so that he can stand on solid roofing at all times. Locate the supporting roof joist by striking the roof with the blunt end of a tool. When the tool hits between the joists, it will have a slight bounce to it, but when it hits above a joist, it will be solid with little or no bounce. Make the cut close to the inside of the selected joist. This will make as large an opening as possible with the least amount of nails to be pulled up. Making the cut just a few inches to the outside of the beam would add many more nails to deal with. For a serious fire in a large area flat roof, your goal is to create an 8 foot by 8 foot or a 10 by 10 foot vent hole. When making this hole, you'll have to divide the opening into smaller sized pieces, usually about 4 by 4 feet each. Also, be sure to make knockout holes at the corners, which are triangular openings at the corners of each section. This will make it much easier to pull up the roof boards. You can begin opening the hole once the 8 foot by 8 foot outline has been cut. It's not usually a good idea to start pulling one cut section before the rest of the cut has been completed, but sometimes you'll have no choice. If you only have one saw, it can take such a long time to complete the cut opening that the interior forces could be driven out of the building because of fire and smoke. Even one small section being pulled will provide some relief inside. If the wind is shifting, make all the cuts before you open up so that you won't be driven off the roof by the smoke and heat if the wind shifts. Sometimes you'll have to make the hole even larger. If practical, do this by cutting as many additional bays between the joists as possible, instead of extending the channel between existing joists. Sometimes it's not just smoke blowing out of the hole that's the problem, it's fire or intense heat. If you still have cuts to make, use a previously cut section of the roof as a shield, which should buy you enough time to make more cuts or to start pulling the next section of the hole. Remember, never put a hose line into any ventilation opening. The hole is there to let all the bad stuff out, and a hose stream from the top will just blow it all back in on the troops below. Plus, it won't cool the burning material under the roof, so it can't put the fire out. When you're working this closely over the seat of the fire, you must continually evaluate the stability of the roof, especially if previous fires or rot have weakened it. The second style of roof is the inverted roof, which was very common in large area flat roofs built from the 1920s to the 1960s. It's similar to the standard flat roof in that it's constructed with a cockloft, with one surface separated from the main roof joist by a light wooden framework. Instead of the ceiling being suspended below the joist by a framework, the roof boards are raised above the joist on a framework of 2x4s. Even though the inverted roof is supported on a lightweight framework, each portion rests directly on a support leading to the main joist at the ceiling level. Even when the 2x4 is burned through, the roof will only drop down a foot or two to the level of the main joists. Because of the way the inverted roof is constructed, it won't feel as solid underfoot as the standard roof does. In fact, it has a definite springy feel to it. This is normal and shouldn't alarm you. You should cut an inverted roof the same way as the standard roof. If using chainsaws, be careful not to make too deep a cut, or else you could sever part of the 2x4 framework. You'll know it's an inverted roof as soon as you make the first hole and see the supports. If you see gusset plates or other types of truss connectors, or if the 2x4s join the top plates at other than right angles, you have a truss roof, and you must evacuate the roof and inform command. On the other hand, if the 2x4s are nailed directly atop the lower supports, it's an inverted roof, and you can continue to operate on it safely. A dangerous relative of the inverted roof is the rain roof. This odd structure can be found on any type of roof, flat, curved, or peaked, of either standard or truss construction. It is built over an existing roof that has become so porous that it no longer keeps the rain out. Many times, people take the cheap way out by leaving the old roof in place and building a whole new one on a raised framework over the original one. This is very dangerous for two reasons. First, the added weight was never designed into the original roof supports, which could be reaching the point of failure. The second reason is that the two layers can significantly delay or entirely prevent venting. The multiple layers create many different places for fire to hide. This can cause you to misjudge the fire's intensity. At the 1978 Waldbaum supermarket fire in Brooklyn, personnel operating on the roof initially reported little heat and no fire coming out of their ventilation openings. The main body of fire was in the cockloft below the original roof, which hadn't been penetrated by the vent holes. The firefighters didn't realize that they were working on top of a very heavy fire in a truss roof. 6 firefighters died in the collapse. Of all the roofs that a firefighter may have to work on, the trusses are the most dangerous. This is because of their lightweight construction. Both flat and pitched roofs can be constructed with either standard or lightweight construction. The main difference between them is the massive beams that carry the dead and live loads. The standard roof is built with larger dimension lumber or heavy steel I-beams. This was the most common type of construction until the 1960s. It's a strong roof that won't suddenly collapse unless the supporting column is destroyed. This type of roof is relatively costly to build, which is why lightweight construction is being used more often. Lightweight construction makes the best use of the truss design. Trusses have been around for hundreds of years, supporting the roofs of churches and cathedrals. A truss makes it possible to span large areas with pieces of material that are much smaller and spaced further apart than a standard beam. This sounds good, but can be very dangerous for firefighters during a fire. There are several reasons for this. The first is that the truss is lighter and made up of thinner materials than a standard beam. When a steel truss, also known as a bar joist, is exposed to fire, it heats up much sooner than a thicker piece would. The second problem centers on the connectors. In a truss, short sections of less expensive material are joined together to cover larger areas. These connectors can be gusset plates, metal pins, or through bolts. During a fire, these connectors can conduct heat to the inside of the material, which is also being burned on the outside. It will be destroyed much faster, which can lead to the truss failing. A truss depends on every one of its pieces to hold it together. This is what poses the greatest danger to firefighters. The destruction of any one of the pieces or the failure of the connectors can cause the entire truss to collapse. Trusses are made up of several elements. They include a top cord, a bottom cord, and web members that connect them. These elements are arranged in a series of triangles that create a rigid shape. As long as they stay joined together, the triangle will stay strong. The top cord supports a compressive load, and the bottom cord, under tension, pulls the top cord into position. The web transmits the load back to the other two at short intervals. This is the key to understanding the danger of truss construction. They only hold their shape as long as the entire structure is intact. If it isn't, the entire truss may suddenly fail, causing the roof or floor to collapse. Picture a hunter's bow as a truss, with the bow as the top cord. If you push down on it, it will flex downward. Once the bowstring is attached and has drawn the bow into its working shape, pushing down on the bow will not affect it. The string under tension keeps the bow pushing back up. Imagine the catastrophic effect that cutting the string would have on a loaded bow. This is what happens to a truss if either cord fails. Trusses of various types are found in most types of lightweight roofs. Since there is a good chance of early roof collapse, you should alert command as soon as you realize you're dealing with a truss roof. Many times, you won't see any obvious signs that the roof is about to collapse until it's too late. Over the last 35 years, dozens of firefighters have been killed when truss roofs failed. You must conduct a well-informed size-up before committing members to the roof or interior operations in lightweight structures. Factors to be considered include the severity of the fire, how long it's been burning, and whether or not the fire has reached the truss. Once heavy fires involve the truss area, it's too late to commit interior forces, especially if there's no civilian life hazard. Of all the modern styles, bowstring truss roofs are the deadliest style of roof construction, and by far the most easily recognized type of lightweight construction. You may not be able to see the classic hump shape form from the street because of a high parapet wall that hides it, but once you reach the roof, you should be able to recognize it. You'll find this type of roof over large floor areas like bowling alleys, car dealerships, and supermarkets. The web and cords are made of 2x6 or 2x10 inch boards that are bolted together. The usual spacing is 20 feet between trusses, so the failure of a single truss can instantly open a 40-foot long hole the full width of the building. The most dangerous bowstring truss is the one that has hip rafters resting on an end wall and on a truss. When the end truss fails, the hip rafters will push out and collapse the end wall. Several firefighters have narrowly escaped death when this happened. The collapse zone at end walls that have rafters resting on a truss and bearing on the wall should be at least 2.5 times the height of the wall. If that is impossible, stay out of the collapse zone and operate instead from flanking positions at the corners of the wall, or from positions above the wall in aerial platforms or from adjoining buildings. Keep in mind that sometimes when one truss fails, other trusses will fall over in domino-like fashion. It's easy to identify a bowstring truss because of its shape, but other styles of trusses are more difficult to recognize. There are a variety of truss designs in different shapes, made by using very light pieces of lumber joined together by various fastening methods. These lightweight trusses can be a parallel cord type for flat use, as in floors or flat roofs, or peaked, which is found in many private dwellings. The most common type of truss has short 2x4s joined together with a stamped sheet metal fastener called a gang nail or gusset plate. Another style consists of 2x4 top and bottom cords connected by tubular steel webs. These steel webs are pieces of tubing that is stamped flat at each end. The top and bottom cords are notched in the center so the flattened end can sit in the cord. A hole is drilled through the side of the cord and a pin is inserted to keep the web connected to the cord. Both of these methods are structurally sound under normal conditions, but have serious implications for firefighters. The biggest problem is their lack of mass to resist fire. If a single 2x4 burns through, the entire truss can fail. To make things even worse, when fire attacks the wood, the gusset plates easily pull out, allowing the truss to collapse. This is because the gusset plates only penetrate the wood about 1/4 inch. The pin drilled into the steel tube and wood cord truss is also dangerous during a fire. Drilling the 3/4 inch hole weakens the narrow dimension of the 2x4, and the steel pin and hole allow the fire to attack the cord from both the inside and outside. Another concern is cutting through the top cord with a power saw blade during ventilation or overhaul. Since these trusses are usually covered with just 1 inch of roofing and plywood, the 2x4 laid on the flat is vulnerable to even a shallow cut. This is a very real danger that could plunge a firefighter through the roof into the fire below. Another problem with open web trusses is the large void spaces they create, sometimes called the truss loft. The parallel cord trusses, which are usually used in place of floor joist, pose a real threat of uncontrolled fire spread. If a fire exposes one truss, the other trusses are almost immediately exposed because there's nothing to stop the spreading fire. The firefighters of tomorrow are going to be paying with their lives for the practice of today's construction industry. You must make every effort to identify buildings with lightweight wood trusses and do everything you can to modify your tactics or create new ones to ensure your safety. Most firefighters know about standard roof and floor systems and their burn time frames and danger signs to look for. In lightweight buildings, you don't have the typical 15 to 20 minutes to search, rescue, and attack before you notice the floor or roof sagging. Many of the new systems fail in less than 10 minutes and drop their entire load without notice. Another danger is the plywood I-beam, the lumber industry's cure for squeaky floorboards. It poses many of the same problems a lightweight system has, mainly the lack of mass. It's made of a top and bottom cord of 1.5 by 2.5 inch plywood, with a web of just 3/8 inch plywood. The I-beam will not show any noticeable sag until it suddenly fails. If roof ventilation is impossible because of the possibility of collapse, then interior operations must also stop. When these structures are occupied, the IC must make a difficult decision. When do you risk firefighters to possibly save the lives of occupants? You have to make a careful evaluation of whether there are any savable victims. Is there fire in the room with the occupants? If so, they're no longer savable. Next, try to find out if the fire has made its way into the voids and if it's attacking the trusses. If so, you should fight the fire from a distance, using the hose stream to extinguish the fire. You must do this before you allow any member to operate directly above or below the damaged trusses. You can use an elevating platform to direct a stream into the truss loft after you open up the building's sidewalls. Provide total window ventilation and operate with the absolute least amount of personnel in the danger area until the trusses have been exposed and examined. Provide emergency shoring if it's needed. CADS-generated reminders of the building's trusses are great pieces of information for today as well as 30 years from now. One very common type of truss roof, especially on commercial buildings, is the metal deck roof. It consists of open web steel bar joists supporting a corrugated metal deck. The primary hazard you can encounter is the danger of falling into the ventilation hole while you're cutting it. That's because of the design of the metal deck and the spacing of the bar joists. You can't know where the joists are below and where the ends of the 4-foot wide steel sheets are. Past experience has shown that these roofs can fail in less than 5 minutes of exposure to heavy fire. The bar joists become seriously weakened when they're exposed to fire, but usually sag instead of snap. Be aware that firefighters advancing below the roof may not be able to see this sag because of heavy smoke or fire and could be at risk. That's why you should use large hose lines on straight stream to sweep the ceilings well ahead of the line's advance. If the steel hasn't already pulled free of its support, it will regain its previous strength when the hose streams cool it. In 2001, the FDNY made an official department policy not to cut metal deck roofs due to the hazards to firefighters. I will not risk a firefighter's life just to save property, but I know that it is possible to operate safely on these roofs. You need to evaluate the fire's involvement and carefully coordinate the fire attack. Use hose lines from areas ahead of the fire to cool the unprotected bar joist and prevent their failure. With the roof supports protected, the roof ventilation team can then safely vent over the operating hose streams, permitting the hose line teams to stop the fire's advance. It is critical that you don't try to cut over the fire due to the danger. If you can't operate on the roof due to a lack of cooling streams, it may be possible to provide some relief by opening sidewalls and operating master streams from an elevating platform basket. Another problem with metal deck roofs is the metal deck roof fire. Once fire exposes the underside of the roof, the metal deck acts like a gigantic frying pan, heating up the layers of hot tar directly above it and pulling flammable gases from the tar. The gases cannot escape upward because of the layers of insulation above them. As the pressure increases, the gases are driven downward through the seams in the deck. Then they are ignited and produce even more gases. The result is a self-accelerating reaction that spreads quickly, dropping little balls of flaming tar on everything below it. The only way to stop the fire from spreading is to cool the bottom of the frying pan, which will prevent the escape of flammable gases. Spray the ceiling with a large stream and ventilate. Now let's talk about the trench cut. This is a specialized cut that should only be used as a defensive tactic. A trench should only be made after a large main vent hole has been completed and pulled. A trench cut consists of 2 parallel cuts from firewall to firewall that are wide enough to allow fire to vent without crossing to the other side, typically at least 3 feet wide. The ceiling below the trench must be pushed down for the entire length and width of the cut to further remove combustibles and allow hose streams to operate into the cockloft to stop fire spread. Making a trench cut takes several steps. First, choose the right location for the trench. It should be close enough to the fire to limit unnecessary extension, but far enough away that you'll have time to complete the cutting and pulling, as well as pushing the ceiling down before the fire reaches it. About 20 to 25 feet should be enough, as long as the fire is below the main vent hole and not closer to the trench. This cut works best if you make it at the narrowest point in the building, so you'll have the least amount of cutting to do. Also, take into consideration the direction of the fire spread. Fire usually travels downwind and spreads fastest from low to high points. Position the trench to block the fire's access to the high points. The next step is to make some examination holes. Position them on the fire side about 5 to 6 feet in front of where you're going to make the trench. Now you can check to make sure the fire hasn't passed the trench area yet and see when to start pulling the trench. Now you're ready to make the trench. Make 2 parallel cuts 3 feet apart from outer wall to outer wall of the building. Don't make the cut any narrower than 3 feet or the fire could just jump right past it. Also, don't make it too much wider than 3 feet because you may have to step back over it. Next, slice the trench into shorter sections, about 4 feet wide, and make triangular knockouts on the fire side so the tools can grab the roofing. Make parallel cuts as close to the outer walls as possible and then work toward the center so that the trench is divided into a series of 4-foot-long sections with knockouts at each section. At this point, all personnel on the fire side of the trench must have at least 2 ways off the roof, not counting crossing the trench. You should also make more examination holes 5 to 6 feet back on the safe side of the trench so that you can check that no fire gets past it. Position 1 or more hose lines below the trench on the safe side and wait until fire shows at the examination holes on the fire side of the trench. Then pull the entire trench and push the ceilings down from the roof. By this point, all interior forces on the fire side of the trench should be withdrawn. You can now use a hose line from the roof or below to drive the fire away from the trench. Remember, we don't operate hose lines into ventilation openings, but a trench cut is a defensive fire stop, not a ventilation opening, and it's acceptable here. The trench cut works best in H-type buildings, garden-type apartment complexes, and other relatively long, narrow structures. It will not work well in very large square structures, such as a supermarket, because it would require too large of a cut to work. There are a few more things to remember when ventilating. First, never ventilate if it means you will expose people or buildings to venting fire. Second, serious fire that threatens a structure demands total ventilation. If you don't let the products of combustion out, they'll drive you out of the structure. Third, more occupancies are now popping up with the newer energy-efficient windows. These seal in the heat, hastening flashover, and have been the cause of death for several firefighters. These windows are also more difficult to vent with a hose stream and even more difficult to clear the sash area out, since the material is usually vinyl or aluminum. The outside ventilation, or OV team, should immediately survey the exterior, locate any victims, locate the seat of the fire, and create firefighter escape routes. Fourth, when you're venting a roof, always be aware of your fellow firefighter, especially the one with the power saw. In poor visibility, toes can be accidentally cut off and limbs slashed. Remember, stop the saw from spinning once it's raised from the cut, and don't gun the engine until you're about to penetrate the roof. Fifth, when visibility is poor on the roof, always use a tool to probe ahead of you. That way you can check for sturdy footing to avoid falling through a hole or walking off the roof. Several firefighters have died walking off roofs in poor visibility. Sixth, some stores in high crime areas have steel plating added to the roof as a security measure. This makes roof ventilation impossible, and you will have to change your usual tactics. Keep in mind that in the event of a serious fire, the roof will collapse early because of the extra weight of the steel. This can also be a problem with heavy snow or ice. Roof operations hold many dangers for firefighters. Only the best personnel should be assigned to this job. Failure to complete the assigned tasks can result in a loss of life or destruction of the building. If you're assigned the roof duty, you're probably operating without the direct supervision of a chief officer. Remember that you will be the eyes and ears of the incident commander. It's imperative that you report any dangerous conditions immediately. Items you should report to your IC include any visible life hazard, the size and shape of the building, particularly the depth, the presence of trusses, the condition of the roof, if it's sagging or spongy, fire burning through the roof, any threatened exposures, the presence of air conditioners or other heavy weights on the roof, and the location of parapet walls, shafts, and setbacks. Failure to do this can result in injury and death to civilians and your fellow firefighters. I hope you've learned something today about ventilation. Use it well. It can save your life. Remember, vent and you shall live. I'm John Norman. Stay safe.